very very early.
Right, thanks. Danny, just to clarify a bit. So you have captured the anomalies of ST in terms of invertible anomalies on one higher dimensional SPT. And
Correct.
do you include also not just the G symmetry, but also like space-time background pro in the sense these are possibly mixed gauge gravity anomaly or even pure gravitational anomaly, that type of anomaly?
So I think, sorry, so we can extend our construction to include spatial symmetries. Whether or not we can look at the gravitational anomaly associated with that, so with spatial symmetries, I haven't thought about that. I'm not sure.
Yeah, these are not necessarily like space-time or spatial translation type of symmetry. It's really like a diffeomorphism.
Right.
Like
yeah.
Reparameterize coordinates or Euclidean rotation or Lorentz group boost rotation, that type of anomaly. I just you have a G symmetry and then you say there are two anomaly G, but I wonder whether you also can include those maybe G mixed with background gravity probes, that type of anomaly.
Right, that's a good question. So our certainly our I'm not sure the answer to that question. Yeah, I
think PIM plus kind of count as also gravitational because time reversal is discrete symmetry acts on the different copy of a Lorentz group if you want. So I think it is what PIM plus is, but I wonder whether you also consider generic, maybe include this maybe this if it's a fermionic rotational symmetry, the Z2F over the SOD rotation, and do you consider all these like spin or PIM plus type of anomaly? That's basically because you say you can capture all. I just wonder what are the type of anomaly it captures.
Right. So we certainly can. I mean, so I think the way that we've let me see what the right thing to say here is.
But Juman, just to clarify, I mean, there are no anomaly associated with spin in 3+1, right?
Yeah, but I say also mix gauge gravity means mix G with the gravitational part.
Yeah, do you have a concrete example? Like what's
in principle, I suppose they should be easy to come up with. Actually,
yeah, I guess it would be helpful if you have some example of the sorts of anomalies that you have in mind.
But I think you have all these people call about the 10 global symmetry.
Yes, that's right.
Plus, those actually I think also has mixed gauge gravity type of anomaly. So at least for those class you have a
right. So I think I guess the way that we've been thinking about this is that for those classes the geometry. So I'm not sure exactly how to phrase this in terms of a gravitational anomaly. I think that's the statement is that I'm not sure how to phrase things in terms of gravitational anomaly. Certainly we can look at invertible anomalies and the way that I guess we can incorporate for example, if you have like a U1 like a U1 like a spin C connection or something like that, or sorry, spin C structure that can be incorporated within our formalism, and by essentially looking at by incorporating it into the GF structure in this way. And here omega-2 is telling you how the fermion parity is embedded in the bosonic part of the symmetry group. I'm not sure if that helps answer your question.
Well, I think I take your answer as actually you do have some. I'm not sure it's a full, but at least I think you do have mixed skew with some either time reversal or some
yeah, that's right.
Yeah, I do think you do have, just not sure.
I think that's right.
General. But you also didn't mention maybe one-point symmetry type anomaly, or you do?
So we're only looking at global symmetries. Our construction doesn't. I'm not sure offhand if we could extend our construction to one-form symmetries, anomalies in one-form symmetries. But our construction is for global symmetries.
Okay. All right. Sorry, just the last one. You have this the Q4, this fake RP4.
Yes.
There's some maybe manifold generator in 4 dimensions. And what does this detect?
I'm sorry?
Does this detect some anomaly? Which anomaly it is? What does it detect?
Sorry. So the statement is that the so if we consider the path integral with a fixed supramodular category input and think of it as a function which outputs a number given a manifold, essentially, then the statement is that this number will be different for RP4 and for Q4. So for RP4, we get this number e to the 2 pi I over 16 times 3. And for fake RP4, we would end up with 8 times, we would end up 2 pi I over 16 times 24, I believe. And so, yeah, the statement is that this path integral, if you just input RP4 versus Q4, you would be able to tell which of those two you had just by computing this number that is associated with from our construction.
Sorry, I'm not sure I get it. Do you try to say this all can distinct the Z16 class?
Yes. Yes.
But
that's correct.
What's something more you can do with this Q4 that the people cannot do? Is there something? I take what you say about homomorphic, but what else can you do with this?
So yeah, so from a physics point of view, the data from RP4 and Q4 is not particularly distinct. You know, if I hand you some supramodular theory with some SET or some SET, the path integral on RP4 and Q4 are going to give you the same the same information. They're both going to give you the Z16 data. It's more the statement that I was making here was more the fact that that if we fix the SET, we can then use the path integral to distinguish different manifolds as well. So kind of flipping it around.
Okay, thank you.
Okay, Ruben.
Hi, I had a question for Roderich. So it's related to Roderich's comment that you showed the Ruby lattice appearing, right? So in your talk, you were focusing on the Heisenberg model. So as we know, in the Ruby lattice, an Ising type model would give more of a dimer type physics, which probably would give similar features. So I was wondering, is this more than a big similarity? For example, could you imagine adiabatically tuning from a type of Heisenberg to an Ising limit? And moreover, could you imagine that the kind of these fingerprints you were showing, kind of these different, you know, in K space, you had these different singularity points. Could you also reinterpret those in a dimer picture naturally, or is that not clear at this point?
Okay, so yeah, so thanks for the question. The relation between Heisenberg and Ising models isn't always simple. You know, so for instance, in the pyrochlore magnet, you get 3 copies of the Ising model for the Heisenberg model. And often the Ising model turns out to look a lot like the Heisenberg model, in particular, if you've got collinear spin states. However, this doesn't generally have to be the case. So, the Ising Kagome model is short-range correlated and non-topological. The Heisenberg Kagome magnet has, this two-component height field and, algebraic correlations and so on and so forth. Well, it's even a bit more complicated than that with order by disorder. But okay, so for the Ruby lattice, I'm not sure we've checked what the Ising model does. Sometimes the dimer picture translates pretty directly in the same kind of gauge field description as in the Heisenberg models, and sometimes it doesn't. And the defects then, for instance, are very different because, you can have three Heisenberg spins add up to 0 in a way that you can't have three Ising spins add up to 0. So that's also related to the Kagome Heisenberg versus Ising difference. Let's see. So there was one last part of your question. Okay, so we are currently looking at a few Ising cases, but as I say, there's no general structure I'm aware of. And for the Ruby lattice, I guess since it's not a planar lattice, it's not immediately obvious that you can solve it exactly. So you might have to do some simulations to check.
Thank you. Just a very quick follow-up on what you said.
Yeah.
Since you said some of these singularities are, I don't know the exact wording you said, something about not being compatible in the Ising system. Is it just that you can't define it? Or is it that the presence of the singularities in the Heisenberg case already tells you it cannot possibly connect to an Ising type?
No, it's really something, often it's something rather pedestrian, which is that if you've got a triangle, you can have three spins add up to 0 if they're Heisenberg spins, but not Ising spins. Mm-hmm. So if you've got a constraint which says the total spin has to be 0, it may simply not be satisfiable by Ising spins. Uh-huh. Right, so remember, if you have a constraint, right, you can ask, are they linearly independent, are they compatible, and so on, but it may be the case that you simply cannot satisfy constraint. This is the difference between, between the word frustration in different communities. Computer science people call frustration free when you can satisfy all the projectors at the same time. Whereas in frustrated magnets, it's more complicated than that. But I think it may simply be, quick answer is it may simply be that a constraint is Heisenberg satisfiable and Ising unsatisfiable.
Thank you very much.
Yeah, I had a very simple question for Roderich. Maybe you said this in your talk, but if you just give me a plot of the structure factor, do I know what topological class that this is in, or are there issues to like the handedness of these nodes that you can't see?
Yeah, so the structure factor doesn't have all the information. So for instance, it doesn't have the charge of the
right.
the charges of the various vortices. So in that sense, we don't have a complete classification yet, in that I could tell you this is all the information you need and you will know everything. So what we have so far is a set of criteria for calling things different, and the structure factor being the same does not imply that they are the same in a sense.
So do you know what the like finer classification or the additional data you would need to look at?
Well, I mean, so minimally the charge, so the vorticity distribution would be the minimal information. The question then is, may there be further constraints, enforced by some other symmetries that you can't, like how you can have arbitrarily complex symmetry protected structures. So it may not be possible, given some symmetry, to displace vortices in a particular way that they can annihilate. So this is something that would be beyond the present description.
Yeah, great. Thank you. Any other questions?
Could I ask a question to Danny?
Yeah, go ahead.
Yeah, thanks for the nice talk, Danny. So this paper you talked about and your other recent paper, they were about having SCTs with H4 anomaly on the boundary of some SPT, right?
Well, so in the bosonic case, it's an H4 anomaly, but in the fermionic case, it can be a more general anomaly. So, for example, this SO3 level 3 case with time reversal should have I think that's even an H1 anomaly.
Let's just go to the bosonic case then, so it's a bit
Mhm.
simpler. So do you have any idea of modifying Cranietta to also capture like H3 obstruction of symmetry actions on the boundary in the general way?
The H3 of GA type obstruction. No, is the simple answer to that. I mean, certainly it would be that might actually be more closely related to the question that Juven was asking about incorporating one form symmetries or into the formalism, something like that. But looking at the or just higher form symmetries in general, we can imagine looking at the symmetry associated to the abelian anion Wilson lines and see if that if there's the higher form symmetry there, and see if that's incorporated somehow. So yeah, perhaps some sort of extension like that would work, but I don't have progress on that to report.
Okay, thanks.
All right, any other final questions? Okay, if not, I think that does it for today, everyone. Thanks to all the speakers, and thanks to everyone for sticking around and listening. See everyone tomorrow.
Thanks.